Okay, let's start to dig some further into this AWS data solution topic. This will be the first of a two-part session in which we discuss the advanced topics about AWS data solution, followed by our overview. Previously, we go over the different services in AWS. Now let's look further. This is called advanced topics, aka data services from a solution architect's point of view. So we are going to look at the services as if they are a combined and integrated part of the AWS infrastructure. We are going to look at how they fit into the whole framework of AWS solution. And we talked about we use the word framework. AWS has something called a well-architected framework, which basically is how you should look at the whole system, the different components, how you should arrange and utilize different components, different web services to make your system functioning well. So there are 5 parts of this well-architected framework. The first is operational excellence, which means you will use all the automation and monitoring and all the tools you have to ensure the operation is smooth and you have a best grip of the system. The second part is the security, and third is reliability, and followed by performance, and finally cost. And our discussion will basically following the same. We are going to start with the physical implementation, how these web services are done inside AWS. And then we will go through operation, we'll go through availability and disaster recovery, then followed by security. And then finally, we are going to talk about elasticity and performance. We are not going to cover cost because basically cost is a combination of your operation and the size. So how much you use to ensure you can operate well. So let's talk about physical implementation first. How is physical implementation achieved? So no matter what web services you are using, no matter what they do, no matter how they are named, all services exist in some form of compute and storage. It must be some kind of compute unit. It must be some CPU plus memory and attach a network interface. Use a network interface to attach to a network so that it can communicate with other components. Then it will work on a data stored in some storage devices. So basically, when we talk about any component or service, we talk about compute and storage. Traditionally, compute and storage are designed in the same compute unit, such as your home PC, such as EC2 instance, such as a non-Aurora RDS. Right? When you design them, when you provision them, you will define the compute, then you will define the storage together to form an instance. A recent trend is to separate compute from storage. So you will have compute component, you will have a storage component. They are separated from each other. And we will explain this very soon. So let's look at the EC2 instance, which is the combination of compute and storage. So in the step 2, the second step, when you provision an EC2 instance, you will define the CPU and you will define the memory. And then also you will define the storage of EBS, of whatever, EBS or others. And in the following step, you will define the size of the EBS storage you will have. Or the other example of putting compute and storage together. It's a non-Aurora RDS implementation. You can see here, when you define an RDS, when you provision an RDS, what you are going to do is you will define a DB instance size. The size will be defined by CPU, RAM, then it will also defined by storage. You will also specify the storage of that RDS instance. Like here, it is a 100 gigabyte. So this is how you put the, this is the traditional way that you put the compute and the storage together when you provision an instance. The trend is moving towards the separation of compute and storage. By doing this, we're referring to, like in RDS, we are moving from an instance-based non-Aurora RDS to Aurora. And then later on, we will even move further to Aurora serverless. Aurora is a relational database that's separating the compute and storage. They do have a server instance, just like non-Aurora RDS. But in this server instance, you do not directly associate, you do not define the storage. It does come with some local storage for operation, but you don't define the database service, the database storage in the instance. Instead, Aurora will store the data on underlying storage device that is separated from the server instance. Each Aurora instance has 6 copies of data. The same data will be copied 6 times across 3 availability zones, which means this storage is spread out in the region. And if you think about the compute part, it's a server instance, which means it must be in somewhere in an availability zone, right? Whereas the storage is spread out to 3 availability zones. There's no way you can combine them together. This separation of compute and storage provides you with a much better disaster recovery capability. And this is the same infrastructure. This separation of compute and storage using a server instance for compute and using multiple copies across availability zones. It's also utilized in AWS Neptune and AWS Document DB. And the AWS DynamoDB is actually similar, but using an early version of this compute storage separation architecture. Another example is Redshift. Oops, I think I accidentally clicked, but basically this is the Aurora implementation. You can see that the underlying gray part is a data copy. It's established across 3 different different availability zone with 6 copies, right? And you have one primary instance, the M instance, that will communicate with the data, underlying data. So this is the compute and the storage separated. Compute resides in one AZ, and storage resides across different AZs. You can even have the compute unit in other AZ, but certainly this is not good for network. So usually this is not the case. And when you define Aurora, you don't need to define storage, because storage is already defined by AWS, and AWS will automatically scale storage. Because when you define Aurora, you only need to define DB instance size. You can see that in the Aurora provisioning window, right after DB instance size, right after you define CPU and RAM, directly under that is availability and duration and durability. You do not need to specify storage anymore. AWS will take care of the storage. AWS will extend the storage if you need more, and shrink storage if you remove a big chunk of data. And we talked about Redshift. Redshift used to have a node type called the DS, the dense storage. these days they are also moving to what they call the RA nodes. These are nodes with two different set of storage. On-node storage, which is the same as before, that you have an EBS drive attached to the Redshift node. You can also extend your storage to S3. So this is a block, AWS block, which happened in December 2019, announcing the incoming of RA3 nodes. And you can see here, it basically says the RA nodes utilizing a new managed storage model that gives you the power to separately optimize your compute power and your storage. So this is the same subject we have been talking about. And also you can have like EMR. In EMR, you can traditionally in the Hadoop system, all your data is stored on node under HDFS, right? But in AMR, you can use a EMRFS data storage, which is S3 based. You store everything in S3. So this is another type of compute and storage separation. So this is a general chain that the compute and the storage are getting separated more and more. Like in RDS, in Aurora, it's already completely done. In Redshift, they are moving towards there, but not there yet. Anyway, that is the trend, right? So we also talked about serverless. You probably also heard about this thing called serverless. Traditionally, our data, our compute happens in a server. And when I say server, it means any form of a compute. It can be a hypervisor. It can be a virtual machine. It can even be a container like KAS, like a Kubernetes pod. So this is a server. Each server is a combination of CPU and memory. You need to, like in EC2 instance or now Aurora RDS, we're already seeing, you need to define how many virtual CPU you need to you want to use, how much memory you will use. A new trend is instead of defining the number of CPU and the memory, you will use a serverless one, where you only specify the processing unit instead of physical CPU and memory. For example, in the Aurora serverless, you can see that instead of DB instance size, you actually have a capacity setting where you can define the minimum capacity unit and the maximum capacity unit. Now, how many unit is enough for your processing? This actually actually requires some try and error in order for you to find the optimized number of compute unit. And also you can see that it actually is not giving you one fixed number of unit. Instead, it gives you a range that it can dynamically adjust. You can do auto scaling. If the performance is not as good, then the unit to that cluster will be increased up to the maximum you define. And if there are like less workload, the capacity unit will decrease until it reaches the balance or it reaches the 1. So this is ideal for unpredictable workload. Like such as when you are in development phase, right? If you are in development phase, you don't know how much you will need, or if you have an unpredictable usage pattern, like you are rolling out something, some online game, for example, you don't know how people will like your game or not. In this case, you probably want to use serverless. Whenever your workload is relatively stable, you probably want to use a server-based solution because serverless is in general more expensive than server-based. And there are too many different types of storage. The most common one, of course, is EBS, the elastic, excuse me, the block storage. And for Aurora Neptune Document DB, as we said, these are managed storage that is duplicated across 3 availability zones. And these are managed by AWS automatically. You do not necessarily need to know where they are, how they are managed. Right? These are that's why they call managed storage. Or like Redshift, they're moving from DS nodes to RA nodes. And there's also a new feature that as we are separating compute and storage, we're also pushing some compute into storage. For example, Redshift Aqua. Redshift Aqua is whatever they call the distributed computing, in storage computing. For a very common usage of Redshift SQL is that you will apply certain filters, especially like character or non-numerical value. Filters like I'm just looking for a city in New York City, for example, city equals to NYC or city equals to Chicago. These are actually operations that you can directly do in storage. Of course, you can say that we can define index, but if it's not an indexed field, then you probably can utilize the storage compute itself and perform this filter inside the compute, inside the storage. Or sometimes when you try to get the full name from first name and the last name, all you are returning is a first name plus a space plus a last name. So this calculation can also be done inside storage. When the data comes from storage into the compute unit, it's already calculated and filtered, or at least part of the work in the SQL query is done. So this is a new feature. I think it's in, as of right now, January 2021, it's still in preview. It's probably still in preview. I need to check that. So we have compute, we have storage. And when we talk about cloud, what do we think of? We think about networking. So you are sharing your AWS resources with other people, other corporations, and even AWS themselves. In order for to define a boundary of your resource, AWS used the term or the concept of virtual private cloud. Virtual private cloud is VPC is a collection of resources that they group together and define this as yours. Right? Each compute unit must exist in the network and has a network interface. And network interface is where the compute unit hits the network. It's the gate between, it's a pathway between the compute unit and the network. That every compute unit, when they try to communicate with other compute unit, the traffic must go from the source unit through the network interface, goes through the network, and get to the target compute unit's network interface, and that's when it enters the target compute unit. And each compute unit can have multiple network interfaces. These network interfaces can be on different network. For example, the web server in the middle of this chart, it has two network interface as the blue dots. And these two blue dots are in different subnets. So this one can have two different IP at the same time, and it can have a totally different access pattern. One could be from the internet, if it's in a public subnet. Another can be just private the gateway that accessing the private subnet. And in this picture, this web server still lives in one single VPC. It's just across two subnets. But in reality, this same thing can happen. The web server can be writing on one VPC between two VPCs. The two network interface it has one can be in one VPC, another being another VPC. This is also achievable. In fact, this is how AWS does its own managed service too. So we already mentioned that the compute unit must be in some network, right? It can be yours or can be AWS. And note here, we also said it can be both, right? So the web server can have a network interface in AWS's managed network. It can also have a network interface in your VPC. In this case, it can both communicate with AWS management system and your resources. If the service exists inside your VPC, which means its compute unit is a compute instance defined in your VPC. It has a network interface that is attached to a subnet in your VPC. And this is true even for Aurora serverless. You may think it's serverless, but still there are some server in some compute unit existing in the system. And this compute unit must reside in the VPC. Don't let the name serverless fool you. It's serverless, but it's not network interfaceless. So this is the example. Like these two EC2 instances, they live in the same VPC, so they can communicate with each other. The network can communicate with each other, whether it's allowed or not. That's a defined using security group, which we'll discuss in the security session. How do you know a resource or a web service is defined within the VPC? When you provision that service, if you see an option to choose the VPC, that's when it's defined inside VPC. And for EC2, you also need to define a subnet because EC2 is just one instance. It has to be existing in one database. It has to be somewhere in the rack, in the machine rack, right? Whereas when you see RDS, when you define RDS, non-Aurora RDS, or actually Aurora RDS too, when you define RDS, you need to define a VPC too, right? That means that RDS instance is inside a VPC. However, you do not define a subnet. Instead, you define a subnet group. This subnet group is a group of multiple subnets across different availability zones. So AWS will automatically pick one subnet and build your RDS there. You do not necessarily need to know which subnet it is in. So this provides you with some flexibility and also provides you with some redundancy, some high available disaster recovery redundancy. So it's still inside VPC, and it is still inside the subnet. Just that this time you don't choose the subnet. AWS will choose it for you. So this is the service. These are for the services that are defined in the VPC. Some services are defined outside the VPC. For example, so its compute unit is not a VPC compute instance, such as EC2, RDS, or Redshift. Instead, it's existing outside your VPC. However, it's in a network managed by AWS, such as DynamoDB, for example. DynamoDB is not defined in your VPC, but it is still somewhere in the network. Otherwise, how would you be able to utilize would you be able to connect to it and run query against it or run insert against it, right? It must be somewhere in the network. And that somewhere is the network managed by AWS. And DynamoDB compute unit has a network interface that is attached to the AWS managed network. and not only DynamoDB. Basically, every web service that exists outside of a VPC has a network interface that is attached to a AWS managed subnet. However, like we said, for services that's outside of the VPC, you can still attach a network interface of a VPC. Thus, it can still be able to communicate with resources in the VPC. But this is one direction. You can only go from the network interface to the VPC, such as like a quick site. If you define a network interface on a quick site or glue, they can access resources in VPC, but the VPC resources cannot access them. On the other side, if you want to access these services from VPC, you will need to define a VPC private link, also called endpoint, so that the VPC resources can access them. Let's take a look at like a glue. When you define glue, you can define a connection. And this connection, this name, I give the name of glue network, and the connection type can be JDBC or some others. And the most relevant to our discussion is a connection type called network. It gives you a VPC for you to choose from. And you will choose the VPC that it will be attached to. This will give your, so when you launch a glue job, this job is basically a compute unit that is created inside the AWS managed network. But AWS will attach a VPC network interface to your VPC to the job if this job is associated with this connection. Now, similarly, on the other side is the endpoint, where if you define an endpoint like Kinesis, then your VPC resources can access that Kinesis through the endpoint. Now, you may be thinking this is painful. Why can't we just define one single access point instead of defining both network interface and endpoint? Why can't we just define one single thing so that they can communicate? For the network interface, it's because the compute units are transient. They exist for a short period of time or for a given amount of time, then they disappear. Next time, when you launch another glue job, for example, the network interface will be different. For this reason, network interface is not a good way for VPC resources to call back to the web service. I believe AWS is also working on something to make this more smooth and more understandable. But at this point, still this is like you have to define two ways for back and forth, for in and out, between VPC and the VPC-less web services. So this is the physical implementation for different web services. We go through compute and storage. We go through network and the network traffic. For computer and storage, we discuss different options of how you handle computer and the service, how you combine them, how you separate them, and then combine them to form a service. And for network interface, network of compute unit, we discuss how data can be, how a service can be related to a certain network, either your VPC or AWS managed network, and how they can communicate with each other. Now let's take a look at operations. Operations are actually a series of tools that is not directly related to any specific web service. For example, we will use CloudFormation for automation and CI/CD pipeline for CI/CD. and the CloudWatch, CloudTrail for logging, something like this. All these topics will show up once or twice in any given specialty exam. So like data analytics exam or database exam, typically in each exam, you will see one question or two regarding cloud formation. You will see one question or two regarding CloudTrail, and probably 2 to 3 questions regarding CloudWatch. CI/CD pipeline is not so much associated with the data-related specialties, but it's closely related to machine learning. So you will see probably 2 or 3 questions regarding CI/CD pipelines in the machine learning specialty exam. So let's quickly take a look at all these. First is the automation. We use CloudFormation for automation. CloudFormation is what they call the infrastructure as code service. You define the infrastructure as a service, as a code. For example, here to the right, you can see that this is how I define a DynamoDB table. You define the type, you define the properties, the attributes, and its key schema. Using code to define your infrastructure makes it easier to maintain and easier to reuse and to reproduce. If you try to create something in a dev, then you want to deploy that to staging and production. Having infrastructure as code is much easier than someone manually typing in everything through console, right? So this is why it's so important to automation, to operational excellence. Anytime you can have automated way of rolling out system, this is definitely better than the manual work. That's why it appears in all specialty exams. And CI/CD stands for continuous integration and continuous development. Then there's one more CD, it's called continuous deployment. AWS has a series of tools, services that you can use for this CI/CD pipeline. You have a code commit. It's basically AWS's version of GitHub, where you can store your source by version in their repository. Then you also have a code build, which is a compile and test and package of your code. Then finally, there's a code deployment, which will help you deploy your code to your specified destination. And finally, when you combine all these three together, you have the code pipeline, which is the integrated service of the whole CI/CD pipeline. There are multiple tools AWS provided for logging and monitoring. We are familiar with CloudTrail, which logs and monitors the API calls within AWS services. And also there's the VPC flow logs, the information about IP traffic going to and from network interfaces in your VPC. So if you have questions regarding how networks queries are flowed and whether your service is going through VPC, is going through a certain network interface, this is where you should look at. And of course, the most important is a CloudWatch. It's so important that it requires 2 slides of its own. The core functionalities of CloudWatch is, first of all, you have a metric collection and monitoring. You're collecting and monitoring all the metrics provided by any service. Then in this process, you can also create log. And finally, you can generate alarms based on the metrics or the logs. So if you think about this, this is just about log and metric, and this both forms a series of time series data. And based on the time series data, you can have alarms. And also CloudWatch log can be defined, can be pushed as a stream. So it can be output into Kinesis stream, and you can utilizing this stream for further analysis. Further on top of these metrics, and logs, this time series data. You also have a series of insights, what they call CloudWatch insights. So for example, Log Insights is an analysis service for logs. Application Insights is monitoring of applications such as Oracle or SQL Server RDS. And Contributor Insights, such as for DynamoDB, for example, which will analyze log data and the time series that display contributor data. And finally, Lambda Insights, apparently it works for Lambda functions performance. So these insights are like plugins built on top of the metrics and the logs, which is the core functionality of CloudWatch. And they will provide you with a further power, especially in the analysis part and the visualization part. Like you want to see the performance of DynamoDB, you can use your contributor insights. And finally, we have anomaly detection. Anomaly detection is also based on the time series data provided by any service. Now, the reason I mention this is because AWS is trying very hard to push their web service into the direction of machine learning, artificial intelligence and machine learning. And they are trying to make sure machine learning is used as much as possible to help their operation as excellent as possible. Now, however, it is hard to utilize machine learning because there are so many different patterns in the usage. So far, the only successful or the widely used machine learning algorithm is an anomaly detection. It used a machine learning algorithm called random cut forest, which will establish a normal baseline of any single time series. And once you have a normal baseline, it's easier for you to identify anomalies. And this anomaly detection algorithm has been widely used in several analytical services. For example, Kinesis Data Analytics and Athena and QuickSight, they all have the ability to run anomaly detection. And CloudWatch has its own version of anomaly detection, which will define based on some log or some metrics where they can find out anything that is it doesn't look right. So this is one of the this actually not one of this is the best most utilized machine learning algorithm inside the AWS operation. Okay, so this is so far we discussed about the physical implementation and the operation, and this concludes the first part of this two-part series of advanced topic discussion. In the next part, we are going to go through availability and disaster recovery, security, and elasticity and performance.